Good day, I'm Norman Wildberger. Today we're going to look at the educational aspects of this new approach to arithmetic that I'm proposing, which in some sense goes back to our first few videos in this series, many years ago now, where we're thinking about a natural number as being represented by a very simple kind of representation of marks on a piece of bark or strokes on a page. And we're making that a little bit more explicit by talking about m sets of units, unit somethings or marks. And we're basically employing an m set or multi-set orientation to define arithmetic, for example, addition like this or multiplication like this. And we've identified this type nat, which represents multi-sets of marks. And I claim that this kind of arithmetic is in some sense more fundamental and more basic than our usual Hindu-Arabic arithmetic that we teach young people, involving the symbols 1, 2, 3, 6, and so on. There's something more primitive and more elementary about this, which I think makes it possibly attractive for educators trying to instill numeracy into very young people. So today we're going to be looking at the issues of naming and ordering these primitive natural numbers, and we want to do it in a way that's largely independent of some higher verbal facility requiring understanding of these Hindu-Arabic numerals. Alright, so since we're human beings, we like to talk and to express ourselves verbally as well as writing things down. So it's natural for us to look to having names for these simple kinds of primitive natural numbers we're talking about. So let's do that now, but perhaps in a somewhat surprising and maybe naive way. Alright, so our first number is 0. This is this empty multiset. Just brackets with a bit of empty space inside. Okay? And we're going to give the traditional name 0 to that. And then the next one is what we're going to call 1. So we just have a single unit something inside our m set. We'll call that 1. And now what about this one? Well, the temptation, of course, is to call it 2. But that's already somewhat sophisticated, the idea of introducing a new name for every next number. What we're going to do rather is to refer to this as 1, 1. Now, we could also call it mark, mark, or unit, unit, but I think it's preferable to actually use 1, 1. This is in keeping with what a young person might want to do. So, technically speaking, this is actually 1 plus 1. It's actually what you get when you take this 1 and you add 1. But let's give it a name and let's call it 1, 1. And similarly, let's call this one 1, 1, 1. And so on. You can see what the pattern is. So this is in fact a base 1 system, if you like. We're really only going to be using these two words, 0 and 1. And everything else is going to be built up from just repeating this particular word. And this is very much in keeping with our expressions, what we're writing down. We're really only writing down two kinds of things, either an empty space or a mark, and we're possibly repeating the marks, everything inside our brackets. So the verbal simplicity is reflecting the written simplicity. Somehow it makes sense. And of course, for a young person, learning this kind of system is, relatively speaking, a piece of cake. This is vastly simpler than learning the standard Hindu-Arabic words 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, and then 12, and then 13, and then 14. I mean, that's all reasonably complicated and takes a fair amount of repetition and learning. In fact, it's not really logically that clear, is it? There's something very logically clear about this system, even though it may be somewhat primitive. So, for example, let us look at the name of this natural number. Okay, what is its name? It is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That is the name of this natural number. Now, we've talked about how the original motivation for natural numbers probably arose in the context of wanting to measure how many of a certain thing there were out in the real world. Maybe antelope at a waterhole. So this is a fundamental usage of numbers, is to measure the size of, well, what we're calling M-sets or multi-sets. Collections of stuff out there in the world. So for example, here is an M-set, which is consisting of these letters. Okay, so even a student who perhaps hasn't learned how to read can still understand that these are things called letters, and, well, that we can count them in the following way. We can just go through the letters, and wherever there's a letter, we can make a mark. So for this letter, we make a mark, and then another one, and then another one, one more, one more, one more, one more. So what we've done is we've replaced each of the objects in this collection that we're interested in with one of our simple unit marks. And we can say that what we've done then is to measure the size of this collection or M-set. So the size of this M-set is this natural number. Now, M-sets in real life don't necessarily have to come in these kind of linear bracketed forms like this. So here might be another kind of example that you could give a young person. So here's a box of some kind, and it has certain objects in it. And the objects are of the pleasant kind, and we might be interested in how big is this box, in the sense of how many things are there in it. So the young person, understanding the strategy, would do the following. He would say, well, what we're going to do is we're going to just create a number out of the box by replacing the objects in here with our unit marks. So I'm going to make a mark there for this thing, a mark there for that heart, a mark there for that diamond, another mark there for that diamond. Let's see, that rectangle gets a mark, that heart gets a mark, that rectangle there gets a mark, and there's a square over there that gets a mark. Right, so I've replaced this multi-set of objects with a multi-set of marks. It's a simplification. So measuring the size of something is some kind of simplification where you just replace objects with our fundamental unit marks. Now this isn't really in the standard form for a natural number, so we would want our student to express this more in keeping with our terminology, so then they would be obliged to organize these marks, right? To write them down in a sequential fashion. And so they'd have to do this in some kind of a reasonable way so they don't get confused. Maybe that one there, and then that one, and that one, that one, that one, that one, that one, that one, and then we'll close the set. So let's observe that counting is actually not really involved here. It's not the case that we are counting how many of these things there are, that we have a prior verbal system for ordering numbers. Rather, what we're doing is we're just replacing objects with marks and then organizing them in a linear fashion. Okay, so it's really prior to what we usually think of as counting. It's some kind of more simple, basic, primeval kind of operation. So to measure an M-set, we just replace each of its elements with a unit something or mark. In other words, one of our little strokes. That's what measuring an M-set means. Now, doing arithmetic with numbers is so familiar to us and ingrained in us that sometimes we're not even aware of relatively basic distinctions. And a very important distinction is that there's these at least two different kinds of roles that numbers play when we're using them to describe the world around us. So numbers, as we've seen, are used to measure the sizes of collections or M-sets. But they can also be used for counting in the sense of ordering. And mathematicians have a name for these different kinds of usages. So we talk about cardinal numbers and ordinal numbers. Okay? So this is somewhat fancy terminology that refers to numbers being used in the context of measuring sizes of M sets, typically. And here, the ordinal numbers referring to counting the position in a list, where you have something ordered and you want to refer to a particular element in that order. So let's give two examples of these different usages of numbers. So a cardinal number usage is one that we've already been looking at. So here is an M set, the M set A, C, D, A, and we're interested in measuring how big that M set is. So that's a cardinal number usage. So we're measuring that set and we're getting that the answer is the number 1111. Okay, so now here's an ordinal number usage where we're referring to not a M set, which is an unordered collection of stuff, but we're actually interested in a list. So here's a list. You can tell it's a list because it has square brackets and it has commas. So the commas are telling us that in this case these elements are ordered. We're starting with A and then B and then C and then D. Over here there were no commas. This is an unordered multiset. If we interchange the order, things would not change. This is a list. The order does matter. So the question here is, what is the 1/1,1th element of this list? The 1/1,1th. We're talking about trying to find the element, not which is the 1th element, and not the 1/1th element, but the 1/1,1th element. And we identify that that is actually C. So this usage of the number 111 is subtly but importantly different from the usage of this number 1111. Okay? Here we're measuring the size, the largeness of a collection or an M set. And here we're specifying the position inside some ordered structure, inside some kind of sequence, which for us is best captured by the idea of a list. Now this ordinal usage of numbers connects naturally with a natural order on natural numbers. So we originally defined natural numbers just in terms of what they are. A natural number is an M set of marks. And we had lots of different kinds of M sets. Now we're observing that our natural numbers can actually be arranged in a very efficient and natural way. We can list them. We can put them in a sequence, starting from the smallest ones and working our way step by step, concretely, one at a time, to bigger and bigger numbers. And here, of course, is this sequence or ordering that we're talking about, where we're starting with, in this case, the empty M set, or 0, and then we have the M set 1, and then 1, 1, and then 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1, 1, 1. And we can keep going. So here the 3 dots refers to the fact that we can go from one to the next by adding 1. That is the systematic way of going from one of these to the next one. We're adding 1. So that leads naturally to this terminology, which is useful, the idea of a successor of a natural number. So if k, say, is a natural number, we'll introduce some abstract letter to represent it. Then its successor is, we might introduce this notation, k prime. That means k plus 1. So this is the number 1, which consists of a single mark. Okay, what's inside here is not the number 1. There's a mark inside, a unit something. This whole thing is the number 1. So for example, here's a number. The number is 11111, and its successor is, well, what you get when you take the number 11111 and you add 1. You add them, you get 111111. So that's the successor. That's the successor of that. And that's really what generates this sequence or this ordering of natural numbers. Okay, so there's now a theorem here that emerges, which is a pretty obvious theorem in some ways, but it's probably useful to lay it out concretely. And let's call it the theorem of induction. Okay. So the theorem of induction is that any natural number can be obtained by starting with the empty M set, 0, and then possibly taking successors. So we've seen that we can start with 0 and then we can take successors. We can get 1, and then we can get 1, 1, and then we can get 1, 1, 1. And what we're stating now is that if we have any natural number, someone writes down a natural number, that it actually is in this sequence somewhere. That if we start with 0, add 1, add 1, add 1, eventually at some point we will get to that natural number that we've written down. So this sequence does not miss some natural number somewhere. Okay, what is the proof? Okay, it's close to being intuitively obvious, but if we had to write something down to convince some maybe young person, we might say the following: that if the natural number that we're starting with is 0 itself, well then it is of this form. It's contained in this prescription because it's the first thing that we're starting with. If it's not 0, that means it contains a mark. And so it can be written as the successor of a number with fewer marks. In other words, it can be written as the successor of the number that we get by removing that mark. And we can then continue to do that. We can continue to find a number of which that is the successor by again removing a mark. So we can go from a natural number that's written down, we can find a finite sequence of numbers, each of which the one that you have is a successor of, and that eventually we get back to the empty set. And that's a consequence of the fact that we've written down a finite number of marks. We've written down a specific number of marks. And so we're going to rub them off one at a time. Well, that's only going to take a certain number of steps, namely the number of marks. And then eventually we will be down to the empty set. So it's a kind of argument that says, all right, given the natural number, we can get back to the empty set in this very concrete prescribed way. All right, so for example, so here is a number. It's the number 1, 1, 1, 1, 1, 1. And we can ask, can this actually be obtained from the empty set, or 0, by taking successors? Well, we would answer that question one way, I think in the natural way, is to take the number that we're given and to write it as the successor of something. We write it as the successor of what we get by removing one of the marks. So this is the successor of 1, 1, 1, 1, 1. And similarly, this thing is the successor of 1, 1, 1, 1, what we get by removing one of the marks. This is the successor of 1, 1, 1. This is the successor of 1, 1. This is the successor of 1. And this is the successor of 0. So the answer is, of course, yes. And we've sort of clearly laid out then what is the sequence that we have to go through to go from the original 0 to the number that we're interested in. We have to go back up this staircase that we've just gone down. So we start with 0, and then we go to 1, and then 1, 1, and then 1, 1, 1, and then 1, 1, 1, 1, and then 1, 1, 1, 1, 1, and then the next step, 1, 1, 1, 1, 1, 1, we get at the number that we've started with. So that, yes, this number actually is in the sequence or the listing or the natural ordering of natural numbers. So when I was younger, there was a very popular TV show for young people called Sesame Street. In fact, maybe it's still around, with lots of funny monsters and characters and so on. But they also had a lot of training or familiarization for students with respect to numbers. So there would be a lot of signs flashing around, like 1, 2, 3, the Hindu-Arabic symbols, and 1 plus 2 is 3, and 3 plus 4 is 7, and so on. And I think that's great because it introduces young people to the idea of numeracy and being familiar with natural numbers. But I'm not so convinced that these are the first steps that young people should go down. I think it's possible that this kind of more primitive number sense, where we just deal with natural numbers in this primitive form, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on, that it's somehow simpler and more in keeping with trying to imbue a numerical sense into young people, independent of a verbal facility that may only come later. So in principle, I think working with these kinds of natural numbers could actually happen at a much earlier age, maybe 2 years old, 3 years old. We could already get young people doing arithmetic in this context. So here are some exercises that we might give students in this direction. Okay? So for example, they might want to find the sizes of these M sets. So here are some collections, and we want to write down what their sizes are. Right? And the important thing is that the students do not yet need to know how to count. Okay? They can do this before they have learned to count. They can write down marks for each one of these things, matching up the objects with marks. Very much the same way that a primitive person at a waterhole might match up antelope with X's on a piece of bark. They can make computations like this. They can calculate what is 111 plus 1111111. And they can write down the answer, and then they can tell you what the answer is, in the sense of the answer is 111111111, or whatever it is. They can do multiplication. They can do addition with more than just two things. So we can get a 3-year-old to understand what's being asked here and to actually make computations. We can ask them to find the successor of some number like this. We can get them to explore the ordinal aspects of numbers. We can ask them for the 11111th element of this sequence. We can ask them to verify some basic law of arithmetic. What is 111 plus 1111111? Is that the same as 1111111 plus 111? In other words, if you interchange these two things, do you still get the same thing? They can verify that if you do this one first and then you do this one on separate pieces of paper and then you compare, lo and behold, you get the same thing. All right, so these are just indicative kinds of examples that I think suggest that it might be interesting to try to get young people engaged in numerical kind of intuition and actual computation at a very early age, at an age that's before they normally do the kind of Hindu-Arabic arithmetic that they currently do. So logically and maybe pedagogically, this primitive natural number arithmetic really ought to come before the Hindu-Arabic arithmetic. In our next video, we do want to turn our attention to the Hindu-Arabic arithmetic, which of course is very important and is practically much more sensible than this is. But still, it's important for us to distinguish between these two kinds of things. So we want to make some space between this primitive natural number arithmetic and the Hindu-Arabic arithmetic. That is for several reasons. One of which is that when we're talking about very, very big numbers, then the Hindu-Arabic system is actually much more powerful, but also correspondingly more problematic to deal with than the primitive one. So we're going to have to explore not just the pros, but also the cons of moving from primitive natural numbers to Hindu-Arabic ones. It's a bit of a trade-off, actually. I hope you'll join me for that. I'm Norbert Wildberger. Thanks for listening.